can't see anybody. Good evening, ladies and gentlemen. Welcome to the national headquarters of the Theosophical Society in America. My name is John Chianchosi. I'm the Director of Public Programs. At this time, I'd like to ask that you turn off your cell phones and other noise-making electronic devices. This evening's lecture is being streamed live, and we welcome friends watching through the internet. The Theosophical Society promotes study, meditation, and service. We encourage open-minded inquiry into the world religions, philosophies, science, and the arts. And we have a deep respect for the unity of all life. Our goal is to help people explore the spiritual path so as to arrive at a deeper understanding regarding the wisdom of the ages. Furthermore, we feel this wisdom is not limited to any one tradition, and thus we offer programs from all traditions. If you have not already done so, I encourage you to take one of our program catalogs where you'll find the programs that are being offered during the coming months. And of course, you can find these programs listed on our website, and there you can register for those that are of special interest to you. The Theosophical Society is a membership organization, and we are always happy to welcome new members. But the programs that we offer here, together with our many resources, are available to the public at large, and everyone is always welcome. We're always happy to see people come and make use of this wonderful campus, and of course come for the programs. This evening I'm very pleased to be able to introduce to you not a regular in the sense of frequent, but a regular in the sense that he has spoken here on a number of occasions. We were just talking, and it seems to be like once a year, and of course we'd like him to come more often. But considering his status and position, we're grateful that he has come tonight. Dr. William Wester is a senior scientist at the Fermilab National Accelerator Laboratory, where he has conducted research on particle collisions and searched for possible new particles that make up the dark matter of the universe. He is also a member of the Dark Energy Survey collaboration, where he studies the particle nature of the cosmos and the expanding universe using a special telescope and scientific camera in Chile. Tonight he has come and he will speak on the search for Planet 9 in our solar system. Please join me in welcoming Dr. William Wester.
Well, thank you. It is very nice to be back here at the Theosophical Society. Not only beautiful grounds, but today in Chicago, it's actually a beautiful day, maybe the third or fourth of the entire year so far. So today, this is going to be a little bit different from previous lectures that I've come and delivered. I hope it's a little bit lighter and a little bit more fun, but also very interesting. And I am going to talk about the search for a possible new planet in our solar system. And as I was sitting and waiting, I was staring at this artist rendition. So this is not the actual planet as we have not yet discovered it, but that's supposed to be the solar system. And it's a beautiful artist rendition. And it just reminds me of those nights when I've gone to the telescope in Chile and been able to look up at the pristine sky and some of the best sky on all the planet. And indeed, the Milky Way is as bright as is shown in this picture. So I would encourage people who have not had a chance, or it has been a long time since you've been out into the dark skies, to take that opportunity and just ponder the intrinsic beauty that is out there. So let me give you a few key takeaways that I hope you leave this lecture. The first is that our solar system is perhaps more complex than you have imagined before, that there is a scientific possibility, or not. We're scientists. Till we know the answer, we are open to all possible hypotheses that a ninth planet in our solar system might exist. That leads to the question, what happened to the previous ninth planet? And I will discuss that. And then just how can you know that something exists that hasn't been seen? So what is the evidence for this ninth planet? In my role as a particle physicist searching for elusive dark matter, I'm very familiar with trying to see something that has not yet been seen. And an additional theme is that I do work on the Dark Energy Survey collaboration. And sometimes the data that you've collected for one project might have some unexpected relevance for an unrelated, profound discovery. So there are many efforts throughout the world investigating basic science, and what we're all sort of yearning for are those breakthrough moments where we break through and discover something new. And it could be a surprise that's waiting to happen. You've set up your apparatus to do one kind of experiment, and maybe the data you collect, you look at it a little funny one day, and you realize, hey, there is something new there. And so that's one of the things that drives us as scientists. So a bit of a disclaimer. It is true I now call myself a particle astrophysicist, but I was trained in high-energy collider physics. That's where we smash particles together at the highest energy. The laboratory that I work, that's about 10 miles away, for 25 years had the highest energy collisions in the entire world. We are now full partners with our sister laboratory in Geneva, Switzerland, where they now collide particles. And we were excited because we discovered the top quark. They were excited because they discovered the Higgs boson. And now it's sort of swinging back to our laboratory here outside of Chicago, where we will be producing more neutrinos and study the mysterious neutrino particle in greater detail than has ever been studied before. I was trained in collider physics, and I did that because I was building detectors made out of silicon to track the particles coming out of those collisions. Well, that experience and the opportunity came to build a new camera for a telescope in Chile, and I now use my training to search for dark matter and to study dark energy. And that was one of the previous lectures that I gave here at the Theosophical Society. I am also a member of the Axion dark matter experiment. The axion is a hypothetical particle. It may still be the dark matter of the universe, and it's a very exciting experiment. I say any day we might wake up and it might be a discovery. So how fun it could be that Dark Energy Survey, this project meant to study dark matter and dark energy, might have something to say about this Planet 9. So we all learned the planets when we were little. So the basic view of the solar system is now that we have the 8 planets and the sun. And so the mnemonic that we all learned is, my very educated mother just served us 9. Actually, now I was looking at this, and if you read that the right way, finally mother gets a piece of pizza as well. She's one of the 9, the 8 planets and the mother sun. The solar system, of course, is more complicated, more complex. Around many of the planets, just like our own, we have our own moon. There are multiple moons around Jupiter and Saturn and the other outer planets. Between Mars and Jupiter, there's an asteroid belt. Ceres is actually a quite large object. Vesta is also large, and so on. And then as you get even farther out, it turns out beyond Neptune, there's another belt of small objects, and there's Pluto. That's called the Kuiper belt. And if you go out even farther, there's an interface between the solar wind as the whole solar system moves through our galaxy. There's a place, the heliosphere, where the solar wind pressure sort of meets the boundary of interstellar space. And that's where things like the Viking and the Pioneer spacecraft are nearby, and those were launched in the 1970s. And there's still useful data that's being analyzed to take a look at this boundary between the interstellar medium. And even farther out from the Kuiper belt and the heliosphere is a possible Oort cloud. It's not known for sure if this actually exists. It's thought to be the source of many icy objects, some of which become comets, long period comets, when they find their way, instead of being way far out, heading towards the sun. That's still only 1/10 of the way to the nearest star. So, again, just to give people an idea of the size of our solar system, let's think of the sun as a basketball. On that scale, Saturn and Jupiter are like golf balls or ping pong balls. The inner planets like our own Earth and Mars and Venus are either the heads of a pin in size or the size of a pea. And maybe Uranus and Neptune are the size of marbles. Here's sort of a distance scale from the sun from all the planets. And when we talk about how far away a planet is, it's convenient to use the unit one astronomical unit. That's how far the Earth is on average from the sun. Mars is at 1.5, Jupiter at 5, Saturn at 10, Uranus at 20, Neptune at 30. To give you some other perspective, the inner planets, you could just get outside this building if you were Mars. If you were Jupiter or Saturn, Jupiter, you would be pretty much still on the grounds of the Theosophical Society. Maybe Saturn would be in the far corner on one of the intersections of the main road. If you head a little farther west, there's a big neighborhood of houses about the size of the grounds of the Theosophical Society. And then beyond that, another large area, a large high school. And so it's sort of, Uranus is sort of at the near edge of that high school, and by the time you get to Neptune, you would be at the far end. So, sun is a basketball. We're talking a solar system that can be, several city blocks. Pluto, which is between 30 and 50 astronomical units, that's not quite to downtown Wheaton. It would take sort of about a 20-minute walk to Pluto. That's not so bad. Now, this planet 9 that I will describe is much farther out, about 10 or 20 times farther than even Pluto. It would take you about 3 to 7 hours to walk to get to planet 9, given that you're already walking faster than the speed of light to get to Pluto. And then you think, okay, wow, that's really something. And then to put it in perspective, the nearest star is like from here to London. So our solar system, even with planet 9, is fairly compact. You do have the Oort cloud that is still gravitationally bound to the sun, but you got to go another factor of 10 or a few to get to the next nearest star. So what about Pluto? It was discovered in 1930, searching for a new planet, and at that time they called it Planet X. And it was named for the Greek god of the underworld, and the name came from an 11-year-old girl. And when she submitted the name, it helped that the initials PL were also the initials of the astronomer who initiated the search for this object. And it's amazing that in 2006, we launched a spacecraft. It took almost 10 years. And in 2015, it flew by and recorded pictures and images. It took months. I remember waiting, like, come on, this has already happened. I can't wait to see what Pluto actually looks like. And it's an amazing object. In the same year that the spacecraft New Horizons was launched, there was a meeting in Prague, Czechoslovakia. This meeting was the 26th General Assembly of International Astronomical Union, and they adopted a number of key resolutions. So here they are voting, and this little body here is empowered and decreed that a planet has a definition, and that definition is that it's a celestial body that orbits the sun. It has sufficient mass that it pulls together all of its mass, and it's essentially a round or an oval shape object. It has the self-gravity determines its shape. And then condition C is that it has cleared out the neighborhood of its orbit, and I'll say a little bit more about that. They also decreed a new category called a dwarf planet, and that includes Ceres. That was the largest former asteroid that I pointed to before. It's interesting, Vesta, the second largest asteroid, is now the largest asteroid and didn't quite make it to dwarf planet. Here's Pluto. Pluto is now considered a dwarf planet. And then there are other objects that have been discovered. These are trans-Neptunian objects, objects that have orbits past the orbit of Neptune. Pluto is one, Eris is one. There could be thousands of these kinds of trans-Neptunian objects, and we've discovered some of the larger ones. There are now 5 of them that have been designated as dwarf planets. There are 6 additional that also appear to be large and are sort of near certain that sometime the next time that these people vote, we'll call them dwarf planets, and maybe 16 more which are highly likely. So before I talk about Planet 9, let me talk about the discovery of Neptune. So people discovered Uranus in 1781, so just after the founding of this country, and they marked the position on the sky where Uranus was observed, and after 40 years, they saw that it was following an orbit not completely as expected, and there was a possibility that beyond Uranus there would be a new planet that was responsible for what I call residuals, the difference between where the predicted orbit of the planet is and where it was actually observed. And this led some very esteemed theorists to calculate and theoretically predict where the new planet might be. And in 1846, note that's sort of just like one period of Uranus to go around the sun, from its initial discovery to now calculating what might be causing its orbit to deviate from a pure, simple orbit. And this is one of the great stories of the history of science. And so Leverrier is generally credited with doing the calculations, so obviously a Frenchman. And at a meeting in France in June 1846, he announced he had gone through, no computers at the time, all these painstakingly complex calculations, no calculators, elementary trigonometry and stuff that anybody can do the simple equation, but to actually do it on a real life problem on this scale was very impressive. So He presented his results, and at the same time at the meeting, there were English astronomers who heard, hey, there might be a new planet to discover, and they knew that they had their own English theorist who was busy at doing essentially the same calculations. Well, it turned out Leverrier could not find a French astronomer to use a telescope, whereas there was lots of pressure and an available telescope in Cambridge. Now, Adams wasn't quite finished with his calculations, and so, he had his bosses hunched over him like, come on, finish the calculation. We're going to go discover a planet tonight. And so there was this real race back and forth. Well, finally, Leverrier gave up on his own countrymen and sent a letter on the 23rd of September to a German astronomer at the Berlin Observatory. Neptune was discovered in less than 1 hour, located less than 1 degree from where the prediction was of Leverrier. This is often touted as an example of the power of theoretical science to make a prediction. Well, so who actually should get the credit? His calculations has merit, his does. Well, I'm going to break the tie tonight and give the credit to the German astronomer, the experimentalist like myself. He had to stay up past midnight and actually go do the real work. So full disclosure, I am an experimentalist. But there's even more to the story. In some sense, the calculations made some assumptions that were not correct. And it was a little bit lucky that Neptune actually turned out to be within 1 degree of that prediction. So let's talk about Pluto. So Pluto's orbit is shown as this inclined orbit. So it doesn't look quite like the other orbits of the planets, which are all more or less in the same plane. In fact, its orbit comes closer to the sun for some period of time than Neptune's. So in fact, from 1979 to 1999, Pluto was actually closer to the sun than Neptune. Here is shown the Kuiper Belt, the region of all those small bodies, and Pluto does not clear out its own orbit. There's not like a big gap of no Kuiper Belt objects because a giant Pluto came through and gravitationally over the millions and millions of years attracted all the other mass around it. It's really one of the same class of objects in this Kuiper Belt. In fact, it has a special relation in its orbit to the orbit of Neptune. It's in what is called a 2 to 3 resonance. And all that means is that twice of Pluto's 248-year-long orbit to go around, that's the same amount of time that Neptune takes to go around 3 times. And it's that connection between the orbit of Neptune and Pluto. Neptune is kind of keeping Pluto's orbit stable over the billions of years of our solar system. And so in fact, if Pluto would be advancing a little bit farther ahead, this 2 to 3 resonance would kind of pull things and straighten things back up. And you can calculate numerically and show that it's a very stable condition. So if you try to look for Pluto from the Earth, it's going to move across the sky. But its motion across the sky is composed of 2 components. The first is, it is moving around the sky, so that's the proper motion. But because the Earth is moving around the sun, and if this is either a nearby star or the planet Pluto, relative to the very distant fixed stars and galaxies, where the star appears in the sky will depend if you're on one side of the sun or the other. You know, if I'm looking at some distant sign and I move my head back and forth, it looks like my finger is moving, even though my finger is stationary. That's the parallax motion of my finger. So on the horizon, it looks like it's just moving back and forth. If I were to look straight up and I'm circling around in a circular orbit, the parallax motion will be a little tiny circle straight above me. And then somewhere in between, it would be an elliptical orbit. So when you look actually on the sky as a function of the day of the year, you see the elliptical part, the parallax motion of Pluto, but then it sort of winds out and the next loop is going to be down here because Pluto does happen to be moving across the sky just very slowly. So if you're going to look for new objects in the solar system, you have to take into account this combined motion, the parallax motion of you, the observer, moving, plus the actual motion of the object itself. So for Pluto, looking for solar system objects, there are a couple techniques. The technique invented early in the 1900s was called the blink comparator. So you take a picture of the sky, and you take another picture of the same region of the sky, in this case 6 nights later, and with this apparatus, you can shift between the two very fast. And if there's an object moving, it will appear to jump. Now, fortunately, it's very hard to see even on my computer screen, but there's a tiny dot in front of this arrow, and if you blink to this next picture, you would see that tiny dot move from there to there. And you could blink back and forth, and it would just jump back and forth. And that's how Pluto was discovered. Now, this has all changed with modern astronomy, using digital cameras and computers. And if the experiment that I'm going to describe, our dark energy survey, we took data on sporadic nights and then came back some period of time later. And it wasn't really conducive to a blink comparator because the time taken apart was sort of random or was more than 6 days apart. But what you can do is look for objects and see if they're consistent with that motion that's both the proper motion and the parallax motion. So let's keep moving outward back to the Kuiper Belt. So the Kuiper Belt, again, is this disk of objects in the solar system beyond Neptune, which was 30 to 50. That's sort of where the range of Pluto. And they're mostly these small bodies composed of different kinds of ices. And I mentioned there perhaps 1,000 have been discovered so far, with many more left. Some are larger, and it's really the 1990s when many of these started to become discovered. A large fraction of these are just like Pluto, not always in a 2 to 3 resonance, but sometimes a 3 to 5 resonance. There's a whole set of different classes of them that all have stable orbits because of their resonant orbits with Neptune. And then I just find it truly amazing that our New Horizons spacecraft continued past Pluto, and just at the beginning of this year flew by one of these objects in the Kuiper Belt. And here it is. It's sort of composed of 2 spheres, one which is 14 miles across, the other is 9 miles across. It's a single sort of dumbbell-shaped object. Even this larger one kind of looks puffy, like maybe it's been composed over the millions of years of coagulating extra large objects together. And so it's a very interesting object, the first of its kind to be studied up close, except for Pluto, which is one of these objects, and it was studied before. So I'll say a few words about the telescope where I have done some work. It is in Chile. about an hour plane flight north of Santiago. It's near a beach resort town called La Serena, which is a very nice place. And then you have about an hour and a half drive up into the mountains. And on the top of the mountain it's still listed as one of the largest telescopes in the world, but it's a 4-meter telescope called the Victor Blanco telescope. And it's now, dates from the 1960s, but that was very important to us because our study of forming the collaboration of over 450 scientists from around the world to study things about cosmology and the expanding universe, we needed to build a massive camera to sit on a massively built telescope. And that's what they did back in the 1960s. They made, out of heavy steel and everything, something that could support a brand new massive instrument. And so just 10 miles away, Fermilab was the leader in the construction of this telescope that got mounted in Chile. And what this telescope does, compared to many of the other famous large telescopes that you've heard of, our goal was to measure more galaxies than have ever been measured before. And to do that, our figure of merit was just not how far or how distant we could appear, but we wanted to cover both a large area and go deep in dimness, in redshift space, in depth of the universe, to cover a large volume of the universe. And every picture that we take, so here's a picture of our focal plane. This is about the size of a hula hoop. Inside your phone, you have a camera. It has about 5 megapixels, but the actual sensor is kind of smaller than your fingernail. Well, we have a whole hula hoop of sensors, and that gives us the exquisite detail that we need. And every picture that we take is a large area of the sky, sort of a hexagon in shape. And just to set the scale, this would be the size of the moon. So if you see the full moon and you say, wow, look how giant the moon looks like tonight, it would still be relatively small on our sensitive camera. Of course, our camera is so sensitive that the moon would cause big problems. It would sort of damage the sensors, and we have protection against us. In fact, the planet Pluto for this telescope is too bright for us to look at unless we take a very short exposure. So our normal length of an exposure, Pluto would sort of saturate. We would be able to do it, but we would see it would saturate the range at which our camera is sensitive. But we take pictures of nice, beautiful galaxies, and it's not these galaxies that we study, but all those little tiny distant dots that are, when the universe was half of its current age. So our survey is to study all these galaxies, and this is a picture of the entire sky kind of folded out. And this is the southern hemisphere, this is the northern hemisphere, so this is the south part of the galaxy. And so we cover a large fraction of the southern part of the galaxy, sort of right in the middle. That's when you're looking straight out the galaxy, where there's not as much dust and everything like that. We also have some areas, and it's sort of like these 3 hexagons, so 3 exposures next to each other, that are our supernova fields. These are special fields that once a week we will go back and observe. And we will try to do the equivalent of that blink comparator, or using our other techniques to see if maybe an exploding star took place. And I'll say a little bit more about that. And the idea is, over the 6 years at which we've collected data, is to build up tile after tile of taking exposures through different colored filters and then 10 tilings, So in most of the area, we have over 50 exposures of the sky. And so if we're going to use this now to look for something moving, we will have that data set to be able to use. So here is one of the ways that we find these supernova, these exploding stars. We do something called difference imaging. So if you look in this middle column, you see some objects, and we have an exposure that we call the search exposure. When we subtract the search exposure from the template, they kind of look the same, but what's left over is a single tiny dot. That tiny dot was an exploding star embedded in this galaxy. So when you do the subtraction, you get, here you can see a near perfect subtraction for this galaxy. Now when you look at this galaxy, instead of a pure subtraction, you're left over with a tiny dot, and that turns to be light from a supernova. In the case of this galaxy, it's the supernova becomes visible. And you can see it as I blink back and forth, you can see this object appear out of nowhere. And it turns out to be a supernova because we studied it. It could have also been a wandering asteroid or some other object moving across the camera at the right moment. The other thing I wanted to point out, there's a little green speck here. We use the raw data from our camera. We don't do any photographic processing until the very end of the process, and there it's very well defined what we do to get the pristine astronomical images. But you can also have little specks of light appear out of nowhere from little defects in the camera or glitters, little small reflections, or many other processes. So to search for, and I'll call them transients, objects that appear out of nowhere. It could be a moving object that appears in one exposure, and then on another exposure it'll appear somewhere else. But all of a sudden, if you've looked at this part of sky, it looks like you have a new object that appeared out of nowhere. Supernova, a star explodes, it'll get bright and then fade away. There are also variable stars that kind of oscillate in how bright they are, and so whether or not they appear depends on when you take the exposure. And then I'll use the scientific term for all those other objects that I'll just call junk. So we can do this difference imaging and subtract a reference exposure, and then sometimes we just find the object appear in a single exposure, and when we look at other exposures, there's no such object. So we have ways to look for this. And again, here is an actual image from our camera. When you see the spike, the diffraction spike pattern, you know that's a star. Essentially every other dot in this exposure is a galaxy. And this is just one corner of one exposure on one of our imaging devices. We do the difference imaging, and we see, a handful of little dots that appear to be above background. And if you stack up a whole bunch of those, you see lots of tiny dots that appear like they appeared out of nowhere. And if you look carefully, you can find the dots of a trans-Neptunian object in this picture. So everybody stare at it for a minute. Can you connect the right ones that satisfy that parallax motion and proper motion? I'll give you a hint. There they are. Anybody get that right? Well, it helps if you draw some lines. That's always a good way to do things. And indeed, this object, has gone around in one of those oval-shaped loops and is starting to move across the sky as well. And Once you get the position and all these little dots line up, you can calculate the orbit and make a prediction where the next dot should be. You'll get it to within some narrow region, and then you can search, and then you can find that dot, and adding that dot to the available information now allows you to even further refine what's known about the object that's shown. This was a fun object. It's a possible dwarf galaxy, maybe very likely. We called it DD. It has this boring name before the Astronomical Union considers whether or not to adopt the name that we gave it. DD for the Dark Energy Survey Distant Dwarf. There it is. And again, it doesn't look like much, a tiny spot. But then you think and you ponder, wow, there's some world out there. And we were the first group to make this discovery. In our supernova fields, we go back to the same area many, many times. And within our collaboration, one of my colleagues at the University of Michigan, we get summer students to come in and think of, hey, what would be a fun summer student project to work on? Well, let's see if we can use the supernova fields, and because we go back so many times and they automatically get the difference imaging performed, we can use that data and possibly look for moving objects. And they soon discovered after that first summer that they had made a discovery of a fair fraction of the trans-Neptunian objects, even though they only used a tiny part of the entire area of our footprint and just the first couple years of data. And I can show as time advances, these are the observations of the different trans-Neptunian objects that were discovered along the eventual fitted orbit. So sometimes, we've then found another exposure that we took over here, and we were able to add that location of the object. And so now we have a whole slew of these, dozens and dozens of these objects that we have now found. The trans-Neptunian objects, the vast majority, live in this Kuiper belt. But in 2003, an object was found. It was discovered, it was a little bit outside the orbit of Pluto. And when its orbital parameters were calculated, there were a couple amazing features of what is now known as Sedna. One is that it has an enormous orbit that goes out hundreds and hundreds of astronomical units. It would take 10,000 years for this object to go around the sun. Another remarkable thing about Sedna is that the closest approach that this orbit makes to the sun is outside the orbit of Neptune. It's far enough outside that it does not have any influence with Neptune. There's no resonance with Neptune. And so that was a great mystery. Well, another object was found similarly, and together there was a suggestion that maybe there's a super Earth, some other planet that might be out there that could keep these orbits stable. And that was all fine, but more and more of these objects got discovered. And the peculiar thing that was noticed is not only do they have these properties where their closest approach is outside the orbit of Neptune, but they all seem to be aligned in one particular direction and in the plane. Now, if you run computer simulations, what would eventually happen is a planet that's on this elliptical orbit would kind of precess around the sun. And so if you have a collection of these objects, you would expect them to be randomly distributed. So in 2016, numerically, a couple professors from Caltech formed the Planet 9 hypothesis by looking at the evidence suggested by these extreme trans-Neptunian objects. The only way that made sense was if there was a Planet 9 acting like Neptune and Pluto, balancing the orbits of all of these guys usually in some sort of resonant configuration or something similar. There were points of stability where these objects would be stable in their current orbits for billions of years rather than wandering around all over the place. Now, when they were doing their calculations, they said, oh, this is all good, that explains these, but we keep getting some other objects that seem to be going off at right angles. And that's when they had their eureka moment, because they discovered other objects going off at sort of right angles. And this was something that they didn't know or tied together. They first saw it in their calculations, and when they did, they said, I really am beginning to believe that this Planet 9 might be possible. So there was even other evidence reported. It turns out there's a mystery of the sun. Instead of the plane of all the planets going around being in the same plane as the sun, which itself revolves, the sunspots move around, the revolution of the sunspots is at like a 6-degree angle. And that's sort of a mystery with people studying the sun. And it turns out that their numbers for Planet 9 kind of fit the hypothesis. Over the billion of years of our solar system, Planet 9 was kind of shifting up slowly the plane of the rest of the planets, and numerically it kind of worked out that you could explain that 6-degree tilt from a Planet 9. So the evidence is mounting. Since that original publication, there have been even more extreme trans-Neptunian objects, the majority of which are also located here. In their calculations, they also found other points of stability, like inside the orbit of Planet 9, the green line. And indeed, there are some trans-Neptunian objects in that stable configuration as well. So everything except the green Planet 9 has been discovered so far. I should just point out, they now have a best fit, taking all that data and running their simulations with the stable orbits. The mass of Planet 9 should be 5 times the mass of the Earth, between 5 and 10 times the mass. It would be on an orbit that is inclined a little bit, just like it's anti-aligned with those inclined extreme trans-Neptunian objects. It goes way out there, almost 500 times the distance between the Sun to the Earth, or 10 times farther out than the planet Pluto. And it would be on a mildly elliptical kind of orbit. It turns out that this new data is now incompatible with explaining the tilt of the Sun. So that's progress in science. There are still mysteries. I almost had you all convinced that Planet 9 existed because of that other piece of evidence. But as scientists, that's one of the things to convey, is that we are open-minded to these refinements as we collect more data. So here is the so-called treasure map, where to look for Planet 9. This is one coordinate on the sky. This is the right ascension, so from vernal equinox looking around all 360 degrees. And this is the declination, how far above or below the plane of all the rotation of the Earth. And so here's the ecliptic plane where all the constellations reside. And as far as we know, we think Planet 9 The typical orbit, their best fit orbit, is shown by this dark line, and it kind of goes near the constellation Orion. Of course, it would be a real shame if it were here. This blue band, that's sort of the plane of our galaxy, and there the stars are so dense it would really be hard to see a planet moving with all the Milky Way stars in between. What this bottom plot shows is how potentially bright, it's actually a very dim object it might be, and we've made searches. Other experiments have searched to about 22nd magnitude, so we don't think Planet 9, which hasn't been observed, we think it must be dimmer than 22nd magnitude, which means it's sort of likely to live on this part of the right ascension. So that's why Orion is highlighted. It's sort of on this part of the sky. And I can superimpose on this footprint of the dark energy survey. And what you see is that the Planet 9 typical orbit goes through our dark energy survey data. So we may have already collected the data where Planet 9 would exist. Our telescope is powerful enough to see the faintness. We just now have to refine that giant connect the dot problem that I showed you before that you all failed. None of you got the right answer on which dots were the right ones. But we can do that now with computers. We are in the process of doing that. And so we are going on all fronts. We are also improving the accuracy when we measure the position of an object on the sky. We are making use of new space telescopes that provide some additional information. We combine that information, and we always work on better rejection of those junk objects. Many of those tiny dots were junk, and if we can remove a large number of those, it makes it easier for the computers to find the right dots to connect. There are other teams that are dedicated now to search for Planet 9. They typically apply, say, hey, Planet 9's still an interesting thing to look for, and they may get 5 to 10 nights on a telescope that other people want to use too, but each year they get about 5 or 10 nights. And if you look at the size, the patch of sky that they can cover in each season, and sometimes the weather is bad and they're out of luck, it could still take 5 to 10 years, I would even say closer to 5 than 10, before they will cover most of the area on that treasure map that is worth covering. So, in the end, if and when it's discovered, I described the great work from those Caltech theorists, how they did all those fancy calculations and made the treasure map based upon these extreme trans-Neptunian objects. I think in the end it'll be many people, including the experimentalist, who actually gets the privilege of possibly connecting the right dots together and identifying Planet 9, but it's really going to take scientists from many areas, and even the theorists will get some of the credit, and deservedly so. So thank you very much.
Thank you, Dr. Wester. Brave new world out there, literally. We do have time for questions, so if anyone wants to ask a question, please raise your hand. I'll bring you the microphone. Or if you'd like to make a comment, either one.
I just had a question. How massive would this object have to be to really affect the orbits? Or does it not really influence it when it's that far out away from the sun?
So that's a very good question. So we think it's about 5 to 10 times the mass of the Earth. And we were very excited when we were starting this enterprise, because on that treasure map, there was another piece of data. There were some scientists that discovered the Cassini space probe, which is in orbit around Saturn and has been there for many, many years. It turns out the Cassini space probe is the most accurately known object that's pretty far out. And when people looked at the orbital data of the Cassini space probe, they noticed some residuals. And the residuals kind of hinted like it was seeing the influence of Planet 9, which again at that time was thought to be closer to 10 times the mass of the Earth rather than 5 times. But it turns out NASA looked at their own data very hard, and there was just some issues with the data at the precision at which the other people were claiming. So it's on sort of the very edge of being able to influence anything in the inner solar system. It's far enough out, it would have negligible effects on the orbits of Neptune and so on. What's of interest, though, is, you know, how did it get out there and things like that. So.
You mentioned, you know, there are all these several kind of off-plane objects, you know, that are, you know, really Neptune orbit objects, right? I mean, so why do we expect that there is this big massive object that is balancing all these tiny 10 objects? You know, why can't 10 small objects be balancing 10 small objects?
Yeah, that's a very good question. Numerically, this fits very well and gives these big regions of stability, and on all those other fronts also explains those perpendicular objects. So that's the only hypothesis that sort of fits all of that data. With that said, there was a scientific paper within the last year that said maybe there's another icy ring where the same amount of mass is distributed around, and looked at that as a hypothesis. And so, you know, as a scientist, we're open to the different possibilities. I would say it, you know, it has a lower probability, but in the end, it's going to be nature that tells us which one is the right hypothesis.
What do you or other scientists believe the 9th planet is made out of?
Yeah, so what is it made out of? That's a very good question. There are different hypotheses about, you know, how could you have such a planet out there? One idea is maybe in the very early formation period of the solar system, there was hot gas all around and protostars forming all around our own sun, which itself was forming. And maybe a planet from one of these nearby stars kind of got captured by our sun. It's a rare thing. Everything has to be exactly right, so it doesn't have a high probability. What I think is going to be very interesting is if we do discover Planet 9, is to find out what it tells us about the formation of our solar system. You know, most of you have heard that there are planets found around other stars. And so that's an exciting field, looking for these exoplanets. It turns out the most common kind of exoplanet is about 5 times the mass of the Earth. And now maybe our solar system would really have such an object. And one of the reasons why you might have a large number of those objects, you know, our planets like Jupiter and Saturn are these sort of big balls of gaseous planet that are around some core. In the early part of the solar system, the current models suggest that some of these planets might have migrated outward, and so we think Planet 9 might be a leftover core that because it had some close encounter with a Jupiter or something, kind of exchanged angular momentum. It's actually a pretty complicated mechanism, but eventually it kind of got thrown out into this much more distant orbit. And so there we might think it's sort of, again, some of these ice gases is a possibility. It's not excluded that it could be rocky in nature. So there's lots of things to study once we have found it.
I'm intrigued by your camera data. That must be quite a challenge so far as storage of data. That must be an enormous footprint.
That's what we do in the land of high energy physics. We, whether it's our collider data, even our neutrino data, and the amount of data that we have with the telescope, the data storage is among some of the world's largest active vaults of data, and it's a privilege to be at the forefront of the technology that enables this kind of science. We work with the Supercomputing Center at the University of Illinois to do our data processing, and to do a lot of our data storage is handled through them.
I actually had a quick question about that. I've learned a lot about the similarities between photography and astronomy. Obviously, I assume that your guys' cameras are a lot more intense. Is the difference really with the light sensors that pick up the images, or I don't know if that makes sense. How do I put it?
So you were asking a little bit more about the details of our camera and what.
Photography cameras.
And the regular photography camera. Right. Yeah, so in many ways it's very similar. We have a shutter that opens and closes. It does it very, very precisely, so that when we collect data from a 100-second exposure and compare it to another, we know that we're getting the same amount of light. So what we're more interested in is calibrating and measuring each of those little tiny dots, whether they're possible new planets or distant galaxies. We want to know generally what wavelength they're brightest in, and we want to know to less than 1% how bright each of those dots are. And so it's everything about our camera is to do that precision work. So for instance, instead of just picking up a camera, our camera is held at very low temperatures, minus 100 degrees, to reduce any kind of intrinsic noise from the electronics reading out the devices. So that's a very important part. So it's all about making the precision measurements of the objects in the sky. And then it's very nice because when you stack the different colors together, you do get these beautiful color pictures as well.
Hi, I'm just curious. You mentioned the program of the 1970s, the Viking program. Supposedly there were two satellites, and one of them went around Saturn and one continued, and that one was out of our solar system. How far do you think? How far do you think that that satellite is right now?
Yeah.
And will it pass by that 9 planet maybe?
Well, so the Viking spacecraft are on a trajectory where they can escape the gravitational pull of the sun, and they have reached that boundary layer between the solar wind pressure and interstellar space. So we now believe that they have effectively left our solar system in that context, in the context of the heliosphere.
So you don't have any data from them?
So we no longer collect imaging data. There is some of the data that they can measure some things that showed that when they passed that transition layer. The New Horizons satellite went by Pluto. It had enough power reserves to do the small adjustments necessary, and it picked the very best candidate next object to go visit. Planet 9 could be anywhere, and there would be no way for a spacecraft heading this way to have enough power to reverse course and try to head over to visit Planet 9. It's still an operating spacecraft. They are trying to decide if it should go try to visit another trans-Neptunian object or things like that. So.
Do we know enough about Planet 9's possible orbit to be able to send a satellite there to possibly reach it?
Yeah, we do not know. The way I describe the calculations that the professors from Caltech did sort of predicted on that treasure map, there's sort of like a 20-degree wide band somewhere in the sky where Planet 9 might be. Now, when an object goes around in an orbit, and if it's an elliptical orbit, it spends most of its time far, far away, and that's when it's dimmer, but that's the direction towards Orion. So that's sort of why they think that's a preferred direction to look. But it's still a large part of the sky, so we don't know where to go looking for it exactly yet.
Now, if I give it to you, you've got to hold it near your mouth.
As a scientist, you don't, I'm sorry, as a scientist, you don't believe that Opaniel, Jehovah, is the region of Jupiter, or Orifiel, Jehovah, is the region of Saturn. You guys don't believe any of that stuff.
Well,
An angel, you know, angels ruling those planets.
yeah. So I do not know how to answer and investigate using the scientific method. One of the reasons why, and I'm happy to end on this personal note, why I do enjoy coming here is because I appreciate the very open nature that this organization proclaims and professes. So with that, thank you very much.
Thank you, Doctor. We greatly appreciate you coming. Very enjoyable. I'd just like to finish with a couple of announcements. One of them is that next week's lecture is going to be on choosing joyful living. That will be by Leslie San. She has spoken here previously as well as taught a couple of workshops. And she will also be teaching a workshop Saturday next week on claiming joy. That's on Saturday, June 1st from 1 to 4 p.m. If you are interested in participating in the workshop, please go to our website and there you can register for it. But if you're not quite sure, at least come for the talk and find out whether you'd like to join the workshop. One last announcement. This week we don't have any programs over the weekend, but we do have our regular meditation class on Sunday. Please take one of these flyers. It's promoting a lecture by Ajahn Brahm, who is quite a highly regarded meditation teacher and Buddhist teacher, traveling internationally often and rarely stopping in Chicago. He's going to be giving a lecture at the College of DuPage on Wednesday, June 19th. If you would like to attend, please take one of these. If you don't want to go, please take a lot of them and give it to other people who may want to go. He's really quite a special quite a special speaker. And he originally is from England, but trained in Thailand, and he's the abbot of a monastery in Perth, Western Australia. And this is his second visit to the Theosophical Society, and we're very happy that he's coming. So please pick up one of those. Thank you again, Dr. Wester. Please stay and have refreshments and continue with the discussion.